I'd like to show you how useful energy can be, and I want to do so by revisiting one of the harder examples we looked at in kinematic equations. The example where we had a car that was going a certain speed and we wanted to find out how far it would travel before it would come to a stop. This was one that took quite a bit of setup and understanding of the problem to solve using just kinematic equations. And I want to show you that by thinking about the energy and the energy alone, we can actually simplify the calculation quite a bit. So here, once again, you can read the problem statement. There are two cars driving. They're identical cars. The only difference is one is driving at 30 meters per second and the other one is driving at 45 meters per second. They're both going to apply their brakes and brake until they come to a stop, and they are identical cars, so they'll have the same rate of braking. Now, one thing I wanted to discuss is how might we see that we could use energy? What would indicate this? Remember that to use energy, we're often going to want to be able to calculate the net work, which is related to the force and some distance for a constant force. And that's a key. For a constant force through some distance, then we could use, this is the relationship. And then also we know that the net work is related to the change in the kinetic energy. And that kinetic energy is going to be the square of our speed. And this is one reason why we really like energy, is because it's the speed, not the velocity. In other words, it doesn't care about direction. And so that and the mass, and so there are some indicators that let us know this. For one thing, you'll notice none of these equations have any time in them. And if we had any questions about time, how long something takes, we could not use energy. But in this case, if we look at this problem, what do we have? We have some speeds. We have an acceleration. Now, there's no accelerations in our energy equations, but we know that acceleration is related to force. And so we can sneakily see that this is going to be related to the work in a roundabout fashion. And so if we can think through the logic, we know we can get work. We've got speeds. The only thing we don't have is mass. And here's where learning to solve things algebraically really pays off. Because maybe we don't need to know the mass. Maybe we do, but maybe we don't. And so this is some things that tell us that this might be a good indication to use energy rather than having to use some other form, say the kinematic equations, which tend to be a bit more cumbersome. Here I've begun to set up my problem. You'll notice I've got my initial velocities all marked and my final velocities all marked, because I'm going to need to use change in kinetic energy. And I'm going to need velocities for that. Okay, what else? I'm just keeping in the back of my mind that I know velocities and I know an acceleration. And so I want to think about this in terms of velocities and accelerations and forces and energy, really in forces and energy. That's what I want. So if I think about the force on my cars, I can tell that they're slowing down. So I know that, for example, if I take car B, it's going to have some force on it. This would be the net force on car B. That's going to be the force that slows it down, that changes its acceleration. And that net force, I know from Newton's second law, has to be the mass of car B times the acceleration of car B. And it's very useful. The acceleration of both cars is the same. These are identical cars. Their mass would be the same as well. Now you might say, but I don't know what the mass is. And that's true, we don't know what the mass is. But even though it's true that I don't know what the mass is, this equation is still true. So I can still write that the net force on my system is the mass times the acceleration. Okay. That net force has to be applied for the entire distance. We know that I'm accelerating uniformly. I'm being slowed down. We should say decelerating uniformly through some distance. Let me just call that dB. So the work done, my displacement is going to be in this direction. My force is in the opposite direction. So the angle between my displacement vector and my force vector is 180 degrees. I should be losing energy, and that's good. That makes sense. Friction slowing me down should be reducing my kinetic energy. Okay. What is then the net work done on car B? So this would be the net work done on B. Well, that's just going to be minus, because I'm losing energy, my force, which is mass times acceleration, times my displacement, which is this dB. That's my net work. Now I can look at the other side, the other half of this problem, and I can say, okay, well, what is the kinetic energy? I'm going to start with kinetic energy equal to V, my initial velocity for car B. I'm going to end with a velocity of 0. So my final kinetic energy is going to be 0. My initial kinetic energy is going to be 1/2 mass times VB1 squared, the speed, right? This is my 45 meters per second. Okay, so the change in kinetic energy has to be 0. That's my final, minus 1/2 mass times my initial velocity squared. And so now I can use work energy theorem, that the net work is equal to the change in kinetic energy, or minus mass times acceleration times my displacement along this trip, the distance that it takes me to slow down, which is the thing I want, has to be equal to 0 minus my initial kinetic energy. And wow, very nicely, you notice there is mass on both sides, so we can divide out the mass. Everybody brought mass. And I can solve for my displacement, and when I do that, I find that my displacement is just the square of my velocity divided by 2 times my acceleration. That's my displacement. That's the distance it took this car to slow down. Notice we didn't have to really worry that much about coordinate systems. We did a little. We had to realize and think about the direction of our displacement and the direction of our force. But for the most part, we didn't have to worry about directions too much. We just had to understand how energy works, and that one force is removing energy, and be careful about the signs of our change in kinetic energy to get this result for my displacement very, very easily and efficiently. So we were able to, with very little fuss, find the stopping distance of the faster car. And when I plugged in my numbers, I got 215.4 meters. That's how long it took the faster moving car to stop. One thing then I can immediately see, though, is that this equation for the stopping distance is going to be exactly the same for my slower moving car. Everything is the same acceleration. The only thing that's going to change is my speed. And so this stopping distance for car A is just going to be the initial velocity for car A squared divided by 2 times the acceleration. And look, I got that without any fuss at all. And when I plug in my numbers, I got 95.7 meters. Now, that's not what I want, really, to answer the question. I wanted the difference in their distances, but that's just, okay, I take the longer distance minus the shorter distance. And when I calculated that, that was 119.7 meters, or about 131 yards. So you can see that, of course, there is quite a big difference in traveling at 45 meters per second, which is about 100 miles per hour, versus 30 meters per second, which is about 70 miles per hour. But it emphasizes how easy it is to get our answer, and we got that quite quickly with very little fuss by considering energy and using work energy theorem rather than trying to go through kinematic equations. We were able to use energy to answer the second question and find out what the distances that these cars traveled, what's the difference in the distances the two cars traveled to stop. We can actually still use energy to answer the first question. How fast would car B be going when it gets here? When the faster moving car, how fast would it be going when it gets to the point where the slower moving car stopped? This would be, we could call it VB2, right? Well, all we need for this is we just need to use energy once again. We know that our net work was minus the mass of our car minus the acceleration times the distance it traveled. This time my distance is going to be shorter. It's going to be the distance car A traveled. Okay. Then I'm just going to work out what my change in kinetic energies are, what my kinetic energy is. My initial kinetic energy, that's 1/2 the mass of my car times this initial velocity squared, or speed squared. And then my my kinetic energy here, call that the final kinetic energy, is 1/2 my mass times the thing I'm interested in, the speed at that point squared. And if I put this together, remember I'm using the net work is equal to the change in kinetic energy. So minus my mass times my acceleration times this 95.7 meters is equal to, I'm going to notice that there is a factor of mass of 1/2 mass in both of these, and so I'm going to factor that out. 1/2 my mass times my final velocity VB2 squared minus my initial velocity VB1 squared. And once again, we're rewarded for solving things algebraically because the mass drops out of both sides, I notice. Notice both sides have mass, cancels out. And I can continue to simplify this and solve for the thing I'm interested in by multiplying both sides by 2. And if I do that, that leaves me with minus 2 times my acceleration times this distance that the slower car traveled is going to be equal to, I'm left with the speed I'm after minus the square of the speed, my initial speed. Okay, look, now all I have to do is add the square of my initial speed to both sides. And what I'm left with should look awfully familiar. It says my final velocity squared, or for my final speed squared, is my initial speed squared minus 2 times my acceleration times the displacement that I went through. Now, that's the same equation we got from the kinematic equations, but we did so without having to set up a whole bunch of distances and worry about a bunch of vectors and other things. The only thing we had to worry about as far as direction was, once again, that our force and our displacement were in opposite directions. And so it made this calculation very, very easy. And when I solved for my speed, I got that I had a final speed for my faster moving car. When it reaches the point where the slower moving car stopped, it was going 33.5 meters per second, much faster than even the 30 meters per second of the slower moving car. Hopefully with this example, you've been able to see how we could leverage what we know about energy, namely that the net work is equal to the change in the kinetic energy of a system, that the net work is the net force applied through some displacement, so long as our net force is constant. And again, in this case, we did pay attention to the fact that there was some angle between them, but we found out that this angle just gave us a -1 sign. So we still were dealing with the fact that we had to use the definition of work, but we could leverage that into a much simpler solution for our problem. We also used the fact that we knew what the kinetic energy is, that it's 1/2 the mass times the speed squared. Now, by applying these ideas, we were able to quickly and easily solve a problem that was much more complicated in trying to use kinematic equations. And so hopefully that this example gives you an idea of the power of using energy, and we'll try to use energy whenever we can. If you have any questions, come see me.